Welcome back, guys. In this video we'll be discussing about the programmable interrupt controller PIC. The chip's number is 8259. As the name suggests, this is a chip that can be connected to your 8085 microprocessor. So as the name suggests, it is for the interrupts, right? It's an interrupt controller which can be programmed, right? So we already know in 8085 this is an additional chip that we can connect. In 8085, in 8085 we actually have 5 interrupting pins, which are the hardware interrupts. You have your trap, RST 7.5, 6.5, 5.5, and finally you have your INTR pin, right? INTR pin. Now you know that all the 4 interrupting pins, trap, RST 7.5, 6.5, 5.5, these are vectored interrupts, right? So we have already discussed what is a vectored interrupt and non-vectored interrupt. Vectored interrupt means it has a specific address, right? Address of what? Address of the interrupt service routine, which means that which is the driver software basically. So for any device that you connect, you will have a driver software, or you can call it as a interrupt service routine. So the device, when it interrupts, the corresponding interrupt service routine, which is a set of code which will be executed in order to service the routine, right? So since you have vectored address means it has a specific address. You can connect only one device to each of these interrupting pins, right? You can connect only one device because the address is fixed. So you can't write the same program at a particular address. You can write 2 programs, right? You can write 2 codes at the same address. Let's say at a particular address you might either write the service routine for your keyboard or for your mouse. You can write both at the same address, right? So only one devices can be connected to these interrupting pins, whereas INTR is a non-vectored interrupt, right? Non-vectored interrupt means it doesn't have a specific address. There is no specific address over here, right? So which means that depending upon the interrupt, you can give the address to the 8085 microprocessor. So that is what we do in this 8259 programmable interrupt controller. Basically the INT pin, this pin will be connected to your INTR of 8085, and whenever the interrupt occurs, the corresponding address of the particular device will be shared with the 8085 address of the ISR, right? There is no specific address for INTR pin, which is a very useful functionality because you can connect multiple devices, right? And depending upon the device that is interrupting, you can give the corresponding address, whereas in the other hardware interrupts, you can control only one device. So let's say your processor, it might require multiple devices. You might be doing even let's say in the case of your PC, your personal computer, you have your keyboard, mouse, you have your 3 USB ports, you have your HDMI port. You can also have more ports, which itself will be more than 5 interrupting devices. Let's say you have a few other devices also connected, then it actually increases the number of pins that is required, right? So this can be solved using the 8259 programmable interrupt controller. So 8259 has 8 interrupting pins. You can see over here IR0, IR1, IR2 all the way up to IR7, which are 8 different pins, which means that you can connect up to 8 devices, right? So with a single 8259 that is connected to your 8085, you can connect up to 8 devices, right? But this is not the maximum that you can connect. What we can do is that you can also make this 8259 as a master, and to all these pins of IR0, IR1, all these pins you can connect at the max up to 88259s as slaves, which means that there is a master which is connected to INTR, and to the master you are connecting 88259s as slaves at these interrupting pins IR0, IR1, IR2. You can connect 8 slaves which are again 8259 chips, and each of these chips again will have 8 interrupting pins. So basically 8 into 8, you can connect up to 64 interrupting devices at the max. That is the maximum capability that you can connect to a single INTR pin of 8085 by using the master slave configuration, right? So let's look a little more deep into this, into the architecture of 8259. So we have first a register that is connected over here, that is known as your interrupt request register, right? IRR. Now this is like a flag, a register. It's a 8-bit register. This IRR is a 8-bit register. By now you might have figured out why this register is, because the name itself suggests interrupt request register. Whenever there is an interrupt in any of these pins, IR0 to IR7, these interrupts will be registered. These interrupts will be registered in this particular interrupt request register. Since we have 8 bits, each bit corresponds to each of these interrupting pins. IR0 has a bit, so 8 bits you have, right? And for IR0 all the way up to IR7, right? So IR0, IR1, IR2, IR1. So if this particular interrupt occurs, that interrupt will be registered over here as 1. If the interrupt doesn't occur, it will be set as 0. It will be cleared, right? By default it will be 0. Whenever an interrupt occurs, this bit will be set to 1, right? So let's say the reason for having such a register is that, let's say if 2 interrupts occur, the interrupt which is having the higher priority will be serviced first. So it doesn't mean that the interrupt which is having lower priority has to be discarded. It won't be discarded, it will be delayed actually. So for taking up the interrupt, once the higher priority interrupt is being serviced, complete servicing, once the 8085 microprocessor completes the servicing of the higher priority interrupt, the lower priority interrupt has to be serviced, right? So the moment the higher priority interrupt is being serviced, what happens? This bit will become 0, and means once it is taken up by the 8085, this bit becomes 0 and the lower priority interrupt will remain. So by default IR0 has the highest priority, IR1 has the next priority, all the way up to IR7. So that is the default priority level order in 8259. So IR0 has the highest priority, the next highest priority is for IR1, then the next highest priority is for IR2, all the way up to IR7. I hope this is clear. But you have the option for changing the order of priority. There are various options which we'll be learning in the coming lectures. So you can initialize the 8259 as per your requirement, but by default IR0 has the highest priority. So we'll be looking at the by default priority level at this point. Once we look into the modes of operations, we will see how these priority levels can be changed and all those things. Now next block over here is known as your priority resolver, right? Priority resolver, the name, as the name suggests, it resolves the priority, which means that the which interrupt is having the higher priority is decided over here. So depending upon the initialization that we have given, it will decide which interrupt has the highest priority. For the time being, we'll take the default priority, and if 2 interrupts occur, so basically it does a few checks, right? It will check which has the highest priority. Then there is another block over here which is known as the interrupt mask register, and there is the third register which is known as the interrupt service register. The priority resolver will check these 3 registers: IRR, which is the interrupt request register, interrupt mask register, and the in service register. So we'll be looking at these registers in detail. So interrupt mask register is again another 8-bit register. each bit corresponds to each interrupt, and each interrupting pin IR0, IR1, IR2 all the way up to IR7, right? So this is IR0's bit, IR1 has another bit all the way up to IR7, right? So 1 2 3 4 5 6 7 8, right? So I hope we have already seen what is masking. Masking means you want to discard a particular interrupt, right? You want to mask the interrupt. So let's say you have connected a device at IR4 and you don't want this interrupt to be serviced at this particular point, right? So you can mask it for a certain period of time, and then maybe at a later point you can unmask it. So you can initialize this IMR register. The moment you put a 1 at IR4, let's say this is IR4, and you put a 1 at this particular bit, and the other bits are set as 0, which means that all the interrupts are unmasked except IR4. IR4 is masked over here, right? IR4 is masked means if this interrupt occurs, this interrupt will not be serviced, it will be discarded, but all the other interrupts will be serviced, right? So that is known as masking. You are masking a particular interrupt and you have unmasked all the other interrupts, right? So the priority resolver, when the interrupt occurs at any of the pin, it will first check if there are two interrupts that are occurring at the same time, it will check which has the highest priority, right? Now the higher priority one will be taken up by the priority resolver. Then it goes into its second check, which is the whether the particular interrupt is masked or unmasked. Let's say if IR4 and IR5 occurs at the same time, IR4 will be taken up first, then it checks the IMR register, which is the interrupt mask register. It finds out that IR4 is masked, so it discards IR4 and then takes up IR5. Again it does the second check, which is the IMR register. It checks whether the IR5 is masked or not. It is unmasked, so it goes to the third check. Now in the third register is known as your in service register, INSR, in service register, which means that it keeps the record of which interrupt is being serviced currently, right? Which interrupt is currently being serviced, right? Now we already have seen that when an interrupt occurs on 8259, it gets registered at interrupt request register. It checks the masking register. Let's say for the time being all the bits in INSR register is 0, right? Which means that there is no interrupts being serviced currently. What happens if there are no interrupts being serviced currently? It will be given to the 8085 through the INT pin, right? It will be given to the 8085 through the INT pin. Now there is a pin over here which is known as the INTA bar, right? Now INTA bar is known as the interrupt acknowledge pin, right? So the 8085, as we have seen, the INTR pin has the lowest priority among the other interrupts. There are 5 interrupting pins. It has the lowest priority. So INTR pin may be serviced or may not be serviced depending upon whether there are any other interrupts of higher priority being serviced currently, right? The moment 8085 is ready to service INTR pin, it gives a acknowledge signal, INTA, interrupt acknowledge, to this particular pin, right? So we have a INTA pin on 8085. So this pin is going to be connected over here, and this pin will give the interrupt acknowledge signal. Now once the interrupt acknowledge signal is given to 8259, 8259 is going to give the opcode of the interrupt, right? The first thing it does is it gives the opcode of the interrupt to 8085. So that is the first process that it gives. Then the 8085 microprocessor gives the next acknowledge signal, right? Interrupt acknowledge signal. With the second interrupt acknowledge signal, the 8259 will give the lower byte of the address. It gives the lower byte. First it gives the opcode with the first INTA signal. So it is an acknowledgement. It is an acknowledgement from the 8085 processor that the interrupt that has been given by 8259 has been taken up. Now you may give the opcode and the address of the ISR. So you have to give the address of the ISR. So this ISR has to be initialized first. So it is the duty of the programmer to initialize the ISR of these devices, interrupt service routine of the devices that you're connecting to the 8259 at the first stage, right? So once you have initialized the address of the ISR, this particular address will be transferred to 8085 when required, right? So once it gives the first acknowledge signal, it gives the opcode. When it gives the second acknowledgement signal, it gives the lower byte of the address. Then it gives a third acknowledgement signal where it gives the higher byte of the address. Now these datas are given using the data bus. The data bus will give the address, opcode, and the higher lower and the higher bytes of the addresses through the data bus. It will be transferred to 8085. This data bus will be connected to the data bus of 8085, right? So this is how it transfers the address. Now let's say if as we said, IR0 occurs, it gives the interrupt signal to 8085. It gets an acknowledgement signal. It gives the opcode, the lower byte, and the higher byte. Now the moment it gives the acknowledgement signal, the in-service register, which is a 8-bit register, each bit is assigned to each of its interrupting devices. So the bit that is corresponding IR0 will become 1, and the bit over here in the interrupt request register, which was 1, becomes 0 the moment the acknowledgement is received from the 8085 microprocessor, right? First this bit becomes 1 and then it converts it into 0 the moment the in-service register becomes 1, right? Now if an interrupt of a lower priority occurs, let's say IR3 occurs, right? IR3 occurs at this particular point while IR0 is being serviced. What happens? The priority resolver checks for other interrupts. Since there are no other interrupts occurring at the same time, IR3 will be taken up, and then it will check for the it will do the second check, which is the masking register, IMR. Since IR3 is not masked, it will approve it, and then it looks for the in-service register. In the in-service register, it finds that the IR0, which is having a higher priority, is being serviced currently, right? Since it is being serviced currently, it will delay the interrupt. It won't give the interrupt signal over here. It will wait till this bit becomes 0. Now this bit becomes 0 when the interrupt is completely being serviced, right? Once it finishes the ISR of IR0, this bit will become 0. Now as a programmer, when you write the interrupt service routine for each of these interrupts, you need to make sure that so this is, let's say this is your main program, and let's say IR0 occurs at this point. What happens? The processor is going to finish the current instruction. The current instruction will be finished, and then it goes into the interrupt service routine of IR0, right? Now IR0 is a program that we have written to service the interrupt at the device that is connected to IR0 pin, right? And once we finish this set of instructions, we have to give a command that is known as end of interrupts command, right? This is an instruction that we have to write, and then we give the return instruction to the program, and then finally it will return back to the main program, right? Now this command is the command that clears the in-service register, right? The in-service register will be cleared. The corresponding bit of the in-service register, in this case it is the IR0. So the IR0 bit the corresponding bit in in-service register will be cleared with this particular instruction, which is the end of interrupts instruction, right? I hope this is clear. Now let's say IR6 is being currently serviced, right? Now let's say we'll take another case where IR6 is being IR6 occurred. It gave the it checked all the 3 checks. The priority resolver it got approved and it gives the interrupt to the 8085, it gets the acknowledgement signal, and finally what happens, this bit becomes, this bit was 1, this becomes 0 now, and the corresponding bit in INSR register becomes 1, right, which means that IR6 is being currently serviced. Now at this point, let's say if there is another interrupt that is occurring, which is IR5, right? Now as we know, IR5 is having higher priority than IR6. This interrupt will be first taken up, it will check for masking. Since it is unmasked, it will go into the INSR register. Now it finds out that the IR6 is being serviced right now, right? IR6 is being serviced, but IR5 has higher priority, right? So since IR5 has higher priority than IR6, it will give an interrupt to the 8085 because it is having a higher priority. Now once the interrupt is given to the 8085, what happens? Now let's look at how it functions. So as we have seen, the main program, let's say this is the main program of that is being executed. IR6 occurred at some particular point, it goes into the interrupt service routine, ISR of the IR6, and let's say while the execution of the ISR of IR6 is happening, another interrupt occurs, IR5. The 8259 gives the interrupt, it will stop the current execution, it will finish the current instruction and it will stop at that particular point. It will jump to the ISR, this is the ISR of IR6, it will jump to the ISR of IR5, right? IR5, it will execute the instructions in IR5, it will finish the instructions. So what happens, this also becomes 1, right? The IR5 in the in service register becomes 1. After the EOI instruction, what happens, it will come back to IR5, right? Sorry, IR6, the interrupt service routine of IR6. So once it comes back with the EOI instruction, what happens, this 1 which was there in service register becomes again 0. Again the instructions in interrupt service routine of IR6 get executed with EOI instruction, but with the end of the interrupt ISR with the EOI instruction, this will also become 0, and then it comes back to the main program. So this is how the interrupts work with 8259 chip. I hope the various blocks are very much clear. Now there is a block which is known as the cascade block. We have already seen that you can operate the 8259 in master and slave mode. So this block will be used for connecting the slaves with the master. So we'll be discussing it when we discuss in detail regarding the cascade configuration and the initialization of 8259. So this is for cascading with in the master slave configuration. Now it is not necessary that you have to have 8 slaves, you can have 1 or 2 slaves, you can have at the max up to 8 slaves, right? Which means that you can connect up to 64 devices. You can have 2 slaves and the rest of the pins connected to other devices, or however you want to. Now you have a read write logic block. Here you can see there is a read signal and write signal, and you have your A0. A0 will also be discussed while discussing the initialization control words. CS bar is chip select. Chip select is for selecting this particular chip. So we'll have a particular address circuit which can select this particular chip whenever you want to write information into this device and when you want to read the information, right? So you need to select this particular chip, so you can connect the address circuit, the address at which you will be connecting the device. I think we have already discussed about memory mapped IO and IO mapped IO. So in that you can have any of the configurations where you can map this device using memory mapped mapping or input output mapping, right? So depending upon the address, you will have to make a address circuit, which means that when that particular address is outputted from the 8085, the corresponding chip is gets selected, right? Now definitely you need to read data. Read data means you are basically reading the opcode, the lower byte of the interrupt service routine, the higher byte of the interrupt service routine from 8259, and write data in the sense you want to initialize the 8259 chip, right? So for that you have to write data into the 8259. So those are done using the initialization control words and operational control words, which we'll be discussing later in the coming lectures, right? I hope this block diagram is completely clear to you guys. Anyway, we'll have a small revision of this particular chip. So we have already seen that this is a chip that can be used to increase the number of interrupting devices, right? So 8085 has 5 interrupting pins: trap, RST 7.5, 6.5, 5.5, and then you have your 5th interrupting pin, which is the non-vectored interrupting pin, that is your INTR. All the other interrupting pins are vectored, which means that it has a very specific address for its interrupt service routine, which means that you can connect only one device to all these interrupting pins, whereas INTR is a non-vectored interrupting pin, which means that there is no specific address for its interrupt service routine, right? To service the interrupt, or the driver software can be written anywhere in the memory, and the advantage is that you as a programmer, or as a you will be initializing these addresses in 8259, the programmable interrupt controller, and these addresses will be given out by the programmable interrupt controller, right? Now whenever an interrupt occurs, first the programmable interrupt controller gives the INT signal and the INT pin over here, and then with the first acknowledgement signal it will gives the opcode of the interrupt. With the second acknowledgement signal it gives the lower byte and the higher byte of the ISR, right? The PIC is going to give the lower byte and the higher byte of the address ISR, because there are 7 different devices that are connected, sorry, 8 different devices, IR0 to IR7. So each device will have a different address. So these addresses are given by PIC, and depending upon which device interrupted, the corresponding address will be given through the data bus. Now you have a interrupt request register which registers the interrupts that are occurring. So let's say if there are 3 interrupts occurring at the same time, all the 3 interrupts will be registered in here. Let's say these 3 interrupts occurred at the same time, and one by one, which is having the higher priority, will be serviced so that you don't miss any of these interrupts. The priority resolver does 3 checks. It first checks the interrupt request register. It finds which is the interrupt which is having the higher priority. It takes up that interrupt. Then it goes into the next check, which is the IMR register, where it checks whether the particular interrupt is masked or unmasked. If the interrupt is masked, then the particular interrupt will be discarded. Finally, it checks the in-service register. In the in-service register, it checks which interrupt is being serviced currently. If an interrupt of higher priority is being serviced, it does not give the interrupt signal. If an interrupt of lower priority is being serviced, then it will give the interrupting signal to 8085. If there are no interrupts that are being serviced, then definitely it gives the interrupt signal to 8085. Let's say if there's one more condition, let's say if IR2 is being serviced and IR2 occurs again while it is being serviced, then obviously it is the same device that is being interrupting the PIC again and again. So the corresponding the second time the device interrupts before the servicing is completed, then the PIC is going to discard the second interrupt, right? Because the corresponding device is being serviced at this particular point, so it does not take a second interrupt from the same device, right? So INSR register keeps the record of which interrupt is being serviced. The moment the acknowledgement signal comes from the 8085, the interrupt request register, the corresponding bit becomes 0, and the INSR register, the interrupt in service register, the corresponding bit will become 1. And when you get the EOI instruction, when the EOI instruction in the interrupt service routine is being executed, the INSR register will clear its corresponding bit, right? So this is how the 8259 PIC or the programmable interrupt controller works. I hope the architecture is clear up till now. If you have any doubts, you can ask me later, or you can message me. I think we'll wind up over here. Thank you guys.